Yes. Hello friends, we'll see the continuation. The another important characteristics of instrument is right as a sensitivity. Then how to define the sensitivity of an instrument? The sensitivity is also called figure of merit. Okay, is also called figure of merit. Figure of merit. That is given as FOM. In general, how to define the sensitivity means if any instrument, even small value is also detected, if there is small change in the input, if there is a detection in the output, then we can say that that instrument is having the high sensitivity. That means the fundamental definition for sensitivity equal to sensitivity S equal to fractional change in output by fractional change in input. Then it is nothing but a sensitivity. There is a fractional change in input, then there is a change in output, then we can say that that instrument is having the high sensitivity. Even though there is change in input, in the output is not detected, we can say that that instrument is not having the high sensitivity. Clear? For example, you take the bridge. Let take any one bridge condition. Take any one bridge. Let this is a Wheatstone bridge. Let this is 10 ohms and this is 10 ohms and this also 10 ohms and this also 10 ohms and this is the galvanometer we are using. Then input is supply voltage. Now under this condition, let assume that bridge is balanced. Now I am changing this input resistance is 10.001 ohm. For 10.001 ohm change in resistance, then with this resistance bridge is unbalanced now. For this unbalance, there must be a voltage across galvanometer. That voltage, because of 10.001, I am getting the voltage in the range of microvolts. Let us assume that. If this microvolts voltage is detected by this galvanometer, then we can say that this is having the high sensitivity. Even though there is a change in resistance, if this galvanometer is not detected, then it is having the less sensitivity. That means for a small change in output, there must be change in output. For a small change in input, there must be change in output. Then it is nothing but a sensitivity. See the difference between resolution and sensitivity. Resolution is change in value which is detected. Sensitivity is change in value which must be detected at output side. That is nothing but this is a ratio. That is nothing but a sensitivity. Okay, don't confuse with resolution and sensitivity. Yes. Listen please. Then point to remember, if any instrument is having high sensitivity, that instruments are more favorable. That means practically instruments with high sensitivity is more favorable or less sensitivity is more favorable. Yes, high sensitivity is more favorable. That means practically instruments with high sensitivity is more favorable. Instruments with high sensitivity is more favorable. One more point to remember, in the selection of instrument, among all the characteristics, the first preference is given to sensitivity. That means in the selection of instruments, among all the characteristics, Character 6. The first preference is given to sensitivity. Yes, the first preference is given to sensitivity. This point also you remember, given to sensitivity. One more point to remember, high sensitivity indicates high accuracy. If any instrument is having high sensitivity, that indicates high accuracy. That's why sensitivity is also one of the supporting characteristics of accuracy. Sensitivity is one of the supporting characteristics of accuracy. Supporting characteristics of accuracy. Characteristics of accuracy. One simple example using bridge itself only. For small change in resistance, the bridge is unbalanced. If it is detected, then we can measure exact value. If small change in resistance, the bridge is not detected, then we can think like this: bridge is unbalanced. For small change in resistance, the galvanometer is not detected. Then we can say that, we can think like this: bridge is balanced condition, even though there is change in resistance. Then we can measure the unknown value, then it is a less accurate. That's why if any instrument is having high sensitivity, measurement is also more accurate. Understood? That's why sensitivity is one of the supporting characteristics of accuracy. Later on, in another statement, there is one concept is there, loading effect. In that loading effect also I will prove that sensitivity is one of the supporting characteristics of accuracy. Understood? Yes. One more point to remember. For example, some instruments are connected in cascade. Let's assume that different instruments are connected in cascade. This is instrument 1 and this is instrument 2. Like this, some instruments are connected in cascade. Instrument 2, then it is instrument 3. Instrument 3. Let the input is Xi. The output of instrument 1 is X1. This is X2 and this is X0. Then what is the sensitivity of instrument 1 is defined. Generally, sensitivity is also taken as output by input, X1 by Xi. Then what is the sensitivity of instrument 2 is defined, X2 by X1. What is the sensitivity of instrument 3 is defined, X0 by X2. It's correct. But I want to define what is the overall system sensitivity. Then overall system sensitivity is S overall sensitivity. How to write? X0 by Xi. Then how to write this X0 by Xi, you tell me? X1 by Xi into X2 by X1 into X0 by X2. You simplify this, again you get this. Then what is the overall system sensitivity? Overall sensitivity equal to what is X1 by Xi? S1, that is S2, S3. That is product of individual sensitivity. That point also you remember. One more point you remember with respect to sensitivity. If any instrument is having high torque to weight ratio, that instrument is having high sensitivity. Later on proof also I will give in the discussion of instrument. Up to now you remember high torque to weight ratio, high torque by weight ratio. If any instrument is designed with a high torque by weight ratio, indicates high sensitivity or high figure of merit. High sensitivity or high figure of merit. Then once you know the sensitivity of instrument, then we can define another factor, that is nothing but a deflection factor. Yes, deflection factor. Then deflection factor equal to 1 by sensitivity. Then we can define deflection factor equal to 1 by sensitivity is nothing but a deflection factor. Clear? Now down, quick. Okay, this about what exactly sensitivity of a instrument. Yes. Okay, clear? Then we go for one more characteristics of instrument. I given accuracy, resolution, linearity. This is sensitivity. I given numbering. I think 3. Change this place, please. That is 4. Numbering is 4. Okay. The next one is fifth characteristics. Okay. By mistake I given. I think it is 3. You change to 4. Okay. Then fifth characteristic is precision of a instrument. Previous one is fourth one. Then you change to this is fifth one. Precision of a instrument. Yes. How to define the precision of a instrument? How to define precision of a instrument? Listen please. For example, we are using 2 voltmeters, 0 to 10 volts voltmeter. The another voltmeter also 0 to 10 volts voltmeter. Both are 0 to 10 volts voltmeter. For this voltmeter, we are giving 5 volts input. Then for this voltmeter also we are giving 5 volts input. This 5 volts input I given 5 times. Repeatedly I am giving. Then 5 times I am getting the readings like this. 2 volts, 2 volts, 2 volts, 2 volts, 2 volts like this. Then this for V2 voltmeter I am giving 5 volts input. 5 times I have given. 5 times I am getting the readings like this. 4.5 volts, 4.3 volts, 4.5 volts, 4.2 volts, 4.1 volt. Like this I am getting. Then this instrument is high precision and less accurate. This instrument is less precision and more accurate. For example, another V3 voltmeter, you take 0 to 10 volts voltmeter. I am giving 5 volts input 5 times. Every time I am getting the readings like this. Then this instrument is high precision and high accuracy. Yes, we can take high precision, less accurate, less precision, more accurate, high precision, high accuracy. But I am talking about what is the precision of an instrument. Yes, precision means reproducibility or consistency in the measurement for same value of input. I am giving 5 volts input 5 times. 5 times I am getting the same reading. It may be true value or it not a true value. That is not the matter. Whatever the reading we are getting for same value of input, if it is repeated, then we can say that is the precision. That means the precision is defined as reproducibility or consistency in the measurement. Note down this definition: reproducibility or consistency in the measurement. For same value of input. Measurement for same value of input is called precision. Input is called precision. Okay, this for the definition of precision. Yes, high precision, less accuracy is possible. Less precision, more accuracy is possible. High precision, high accuracy is also possible. But point to remember, high precision does not indicate high accuracy. But here I taken 4.5, 4.3, 4.5, 4.2, 4.1. When I don't consider any decimal point, I will take 444. This also indicates high precision. That means, point to remember, all accurate instruments, all precise instruments may not be accurate, but all accurate instruments may be precise. Important statement. If it is accurate, there is a possibility of precision also, but it is high precision, not guarantee for high accuracy. That's why all precise instruments may not be accurate, but all accurate instruments may be precise. Accurate instruments may be precise. That point to remember. One more point. In the measurement of any value, if that value is having more number of significant figures, then that measured value will be more repeat. For example, we are measuring 2.5 volts, we are measuring 4.53 volts. This 4.53 volts may be more repeated as compared to 2.5 volts. Because it is more number of, this is the 3 significant figures, it is the 2 significant figures. How to count the number of significant figures? There is some mathematical rules are there that I will explain. By using that mathematical rules, then you can count the number of significant figures. That means, if the number of significant figures are increases, important statement to solve the problems. If the number of significant figures are increases, then precision. If the number of significant figures are increases, precision is also increases. If any number is having more number of significant figures, that number will be more repeat. Okay. Then one more point to remember. Precision index indicates deviation of repeated values from the central value. This is important. Precision index indicates deviation of repeated values from central value. What is the meaning of this? Which is the central value? True value is the central value. This repeated value deviates from central value by 3 volts. That's the precision index. This is deviated 0.5 volts. This is deviated 0.7 volts. This is deviated like that. That is nothing but a precision index. The precision index indicates deviation of repeated value from center. There is a formula for precision index is there that I will give in the statistical analysis. But up to now, you remember this point. Yes. If the number of significant figures are increases, precision is also increases. One more point to remember. As a formula, precision is given as precision equal to measured range by standard deviation. Okay, measured range by standard deviation. This one formula for precision, standard deviation. measure range by standard deviation. Okay, note down quick. Okay, this about what exactly precision of an instrument. See, all precise instruments may not be accurate, all accurate instruments may be precise. For this, I am giving one example. For example, you know this. What is the value of pi? Pi equal to 3.14. Is it exact value? No. The exact value of pi equal to 22 by 7. This is 3.14115926536. This exact value of pi. Now tell me, is it a more accurate? No, but it is a more accurate value. More accurate value. But it is a less accurate. Now, here the number of significant figures are more or less? More. Here the number of significant figures are less. How to count number of? I will explain. That means, if the number of significant figures are more, accuracy is, sorry, if number of significant figures are more, what the precision is also more. That's why, because this is more accurate and high precision, but it is less accuracy and less precision. That's why all accurate instruments may be precise. Precision, high accuracy indicates high precision, but high precision may not guarantee the high accuracy. Clear the example? This is accurate value and more number of significant figures. If the number of significant figures are more, accuracy is also, precision is also more. That's why because of high accuracy, we are getting high precision also. Understood? This point you remember. Okay, this about in detail what exactly precision of a instrument. With this, I explained about what is accuracy and resolution, linearity, sensitivity, and other one is precision of an instrument. But I told that how to count the number of significant figures in a given number. This knowledge is important to measure given value is which is more precision. That's why how to count the number of significant figures in a given number. Right on? I told that some mathematical rules are applied to count the number of significant figures in a given number. What is that rules that you note down? Yes. To count the number of significant figures in a given number, to count the number of significant figures yes, in a given number, yes, following mathematical rules are applied. Following mathematical rules are applied. Yes. What are the mathematical rules we can apply to count the number of significant figures in a given number? One is, listen please. If the decimal point is present or absent, these rules you note down. How to apply these rules, that I will give some examples. If the decimal point is present or absent, the leftmost digit which is non-zero, yes, the leftmost digit which is non-zero, is most significant digit. That means always which is non-zero is most significant digit, and that is the leftmost digit is most significant digit. If the decimal point is absent, the rightmost digit, which is non-zero, is least significant digit. If the decimal point is absent, the rightmost digit, least significant digit also non-zero. Yes. If the decimal point is present, either the leftmost digit, sorry, the rightmost digit, not leftmost, the rightmost digit, yes, the rightmost digit, either 0 or non-zero, is least significant digit. Yes. Every digit in between most significant and least significant is the significant digit. Every digit, yes, in between most significant and least significant is significant digit. Every digit in between most significant and least significant is significant digit. These points you remember to find the number of significant figures in a given number. For example, if any resistance is measured like this, 115 ohms, then how many number of significant figures in this number, in this representation? Yes. If the decimal point is present or absent, always non-zero is the most significant digit. Leftmost non-zero is the most significant digit. That's why always the left side which is non-zero is there, that is most significant digit. If the decimal point is absent, non-zero is the least significant, rightmost. Every digit in between most significant and least significant is significant. Then how many significant figures? 3 significant figures. Clear? Okay. For example, example 2. If it is given like this, 135.0 ohms we are measuring. How many number of significant figures? If the decimal point is present or absent, the leftmost which is non-zero is the most significant digit. But the case is decimal point is present. If the decimal point is present, the rightmost digit, either 0 or non-zero, is least significant. Non-zero is also, 0 is also least significant, because if the decimal point is present. Sir, why you take like that means? Simple. 135 is close to 135.1, or it may be close to 134.9. There is change in 0 na. 0 is affected na. That's why 0 is also significant. Clear? That's why the number of significant figures, every digit in between most significant and least significant is significant. Number of significant figures are 4. For example, 0.143 volts it is given. How many number of significant figures? Yes. If the decimal point is present or absent, always non-zero is the most significant. That's the reason why 0 is not most significant, 1 is most significant. Then 3 is least significant. Every digit in between most significant and least significant is significant. Then how many number of significant figures? 3 significant figures. Simple. Sir, why you are not considering 0? Simple. 0.143 close to 142 or 144. Is there an effect of 0? No. But it is close to 135.1, 134.9. This is affected, but this is not affected. That's how many number of significant figures? 3 significant figures. Clear? For example, if it is given like this, 10350 volts, how many number of significant figures? Yes. Always leftmost is the most significant. Here decimal point is not present. If the decimal point is not present, non-zero is the least significant. If the decimal point is absent, the rightmost is which is non-zero, not the 0. That's why 5 is. Then every digit in between most significant and least significant is significant. Then how many number of significant figures? 4 significant. It's not a 5. This is important. This is 4 significant figures. This also you write like this now. 1035 into 10 power 1 also you write. Then how many number of significant figures? 4 significant figures. Like that also you write. For example, 1035 into 10 or 0.1035 or 10.35 into 10 cube volts. Like this it is given. How many number of significant figures? If it is given in 10 cube like this, no need to consider. 1, 2, 3, 4 significant figures. 4 significant figures. If it is given like this, 0.012 into 10 cube it is given. Then how many number of significant figures? No need to consider this one. Then which is most significant? 1 is most. Which is least significant? 2. How many significant figures? 2 significant figures. If it is given like this, 0.00035 mega ohms it is given. How many number of significant figures? You multiply with mega ohms means into 10 power 6 we can get 35. Or directly also we can measure how many number of significant figures? 2 significant figures. Like this we can write. Among all these, the number which is having the more number of significant figures, that will more repeat. That is nothing but a precision, high precision. Understood? Like this we can count the number of significant figures by applying these mathematical rules. But one more point to remember, by using dark dots method also we can define the accuracy. For example, this is central value and this is values deviated from the central value. Okay, the dots are here. If these dots are here like this, this is the measured values. Let us assume that these are very close. Then these dots are away from the central value now. That's why it is high precision, less accuracy. This you take high precision, less accuracy. By using dot methods also, we can define the accuracy. For example, this is the central value. Okay, all the dots, repeated values are here. Then this indicates that high accuracy and high precision. High accuracy and high precision. Central value is true value. This is the measured values. All these measured values are very near. That's why it is a high precision. But away from central value, no, that's why less accuracy. This is very near and it is within the true value. That's why it is high accuracy and high precision. For example, if it is given like this. Then what this? This is less precision, less accuracy. Less precision and less accuracy. Less precision. All these values are away and this is not nearer to true value. If all these dots are within this circle, this central circle, okay, here, and it is not at same and different position, then that indicates that high accuracy, less precision. Understood? Okay, like that we can define this. By using black dots also we can make the measurement of accuracy. We can define the accuracy. Understood? Sorry, we can define the precision. Okay, but here I am telling what is the precision, what is the accuracy also. By relating this we are specifying. Okay, this about what exactly precision of an instrument. With this I explain about what is accuracy, what is resolution, linearity, sensitivity and precision of an instrument. The another desirable characteristics of instrument is repeatability, reproducibility and range and span of a instrument. That you will see. The sixth characteristic is repeatability and reproducibility. Take this is repeatability and reproducibility. Tell me, what is the repeatability and reproducibility of an instrument? Repeatability, reproducibility, both are precision indication. The name itself it indicates that. Repeatability of instrument, reproducibility of instrument, both the terms indicate the precision. But the concept in repeatability, concept in reproducibility is different. For example, I am doing one experiment. I am measuring 5 volts. In that experiment I am measuring 5 volts. This 5 volts input I given 5 times. Every time I am getting the same reading. Then we can say that that is the repeatability. I am doing one experiment. In that experiment I am giving some input. For a given value of input, same input I given 5 times using same instrument at same condition at same time. Not different times, not different instrument, not different condition. All these are at same time only. All the inputs I given at same time using same instrument. For same value of input, I am getting the outputs like this. Every time I am getting the same value. Okay, then it is nothing but a repeatability. Then what is reproducibility? If this 5 volts, I am not only measuring, different persons it is measuring, different users it is measuring. For example, 10 members conducting same experiment. 10 members are conducting same experiment. use 10 members are using different instruments. They are not using same instruments. Understood? And they are conducting this experiment at different conditions, at different times. Then all the persons, all the users are giving same input. And using different instrument at different conditions, if all the users are giving same input and all the users are getting equal outputs, then it is called reproducibility. See the difference. Repeatability is with respect to single user, but reproducibility is with respect to different users. But both are precision indication, but concept is different. Then what is the repeatability? What is the reproducibility? That is the difference. Okay, you write down this one, repeatability. Note down this. If one experiment is conducted by one user, using same instrument at same condition at same time, for same value of input, if the output is repeated, then it is called repeatability. Yes. Note down what is the reproducibility. Put heading reproducibility. Yes. Right on. If one experiment is conducted by different users, using different instruments at different times and different conditions, for equal values of inputs, if all the users are getting the same reading, then it is called reproducibility. Okay, this about what exactly repeatability and reproducibility. That statements you remember. Then one more character 6. This also desirable static character 6 of instrument. What is the range of instrument and what is the span of instrument? How to define range of instrument and how to define span of instrument? Yes. The point to remember, the range is in the representation. It is represented. Range is represented minima to maxima. As a representation, it is represented minima to maxima. As a value, a full scale reading is called range. A full scale reading is called range of instrument. Reading is called range. As a value means you take this. As a representation means you take minima to maxima. What is the span of instrument? How to define span of instrument? It is represented. Yes. It is represented maxima to minima. As a value, span equal to absolute value of maxima minus minima is nothing but a span of an instrument. See the representation and you want to value. Represented means maxima to minima, it is represent. Span means absolute value of maxima minus minima. That is nothing but a span of an instrument. For example, here I am giving two examples. A voltmeter measures A voltmeter measures 0 to 150 volts. A voltmeter measures 0 to 150 volts. Then what is the range? As a representation 0 to 150. Then what is the value? As a value 150 volts. What is the span? As a representation 150 to 0, maxima to minima. What is the value? 150 minus 0. How much you get? 150 volts. As a representation it may be different, but here value range equal to span we are getting. But you don't think like this every time range equal to span. That depends on the calibration. A voltmeter is calibrated as 0 to 150 volts. What is the range? What is the span? It is a representation, it is a value. It is a representation, it is a value. But you don't think every time range equal to span. For example, you take the example 2. A thermistor measures. A thermistor measures a temperature of minus 20 degrees centigrade to 80 degrees centigrade. Or a thermistor is calibrated as minus 20 degrees centigrade to 80 degrees centigrade. Now what is the range? Range is as a representation minus 20 to 80 degrees centigrade. Add the value 80 degrees centigrade. This is representation, this is the value. What is the span? Span equal to how it is represented. 80 degrees centigrade to minus 20 degrees centigrade. Maxima to minima it is represented. As a value, span equal to absolute value of maxima minus minima. Then how much we can get? 100 degrees centigrade. 100 degrees centigrade. See here how much range we are getting? 80 degrees centigrade. How much span we are getting here? 100. Is it range equal to span? No. That's why every time range is not equal to span. That depends on the calibration of the scale. That is depends on the calibration. Okay. This about what the range and span of instrument, what the repeatability and reproducibility of a instrument. With this, accuracy, resolution, precision, linearity, sensitivity, reproducibility, repeatability, range, span, all these characteristics are completed. All these characteristics are which characteristics? Desirable static characteristics of an instrument. Desirable static characteristics of an instrument. During design of instrument, we can design in such a way that we want to get these characteristics. Like that we can design. But after design, due to usage, due to instruments we are using, due to materials we are using, we are getting some undesirable characteristics also. Now, what is that undesirable characteristics of instrument? That I want to discuss. That I given list out now. What is the hysteresis of instrument, dead zone, dead time, threshold of instrument, and drift of instrument, static error of instrument, that I want to discuss. Okay. The next session will continue with what is undesirable characteristics, undesirable static characteristics. Then we go for, with that undesirable static characteristics, the static characteristics will be completed. Then we will start the dynamic characteristics of instrument also. Clear? Okay. Understand? Okay. Concentrate.